Stronger than diamond, lighter than paper, more conductive than copper, but still more pliable than rubber. All in one extraordinary material. Sounds like the stuff of comic books or fairy tales. But with the technology of 2D materials, it is a reality. The astounding properties of 2D materials have only just begun to reveal themselves. And as we delve deeper into this developing technology, we discover many important applications for New Zealand and the wider world. In simple terms, a 2D material is a bound lattice of atoms along a single plane. Essentially, a sheet of material just a single atom thick. When we work with these materials, we begin to discover a number of extraordinary properties. Take graphene, for example. Graphene is a 2D material made out of a hexagonal lattice of carbon atoms, much like chicken wire, only on a molecular level. For many years, it was believed that this single layer of carbon would just be too volatile and could not be isolated. But in 2004, the researchers Andrei Geim and Konstantin Novoselov managed to do just that with simply a pencil and some sticky tape. The graphite used in pencil leads is essentially layer upon layer upon layer of graphene. By separating out these layers, again and again, you eventually get graphene. Andrei and Konstantin managed to do this by placing a graphite flake on some sticky tape and then using another piece of tape to cleave it in half. When repeated over and over, the researchers were astonished to find that in some cases, the resulting fragments would just be a single atom thick, and thus graphene. But what makes this so special? One of the properties of graphene that makes it so useful is its extreme conductivity. Because carbon has 4 electrons in its outer shell, and in the hexagonal lattice, 3 of the 4 are bound to other carbon atoms, there is only 1 electron left free from every carbon atom. This creates a so-called electrical highway for conduction of electricity, and because of the perfect 2-dimensional hexagonal lattice of graphene, there is very little to interfere with the path of these electrons, meaning that there is only minuscule resistance even at room temperature. Another characteristic of graphene is its Hulk-like strength, but Tinkerbell-like weight. Graphene is said to be so light that a sheet the size of a football pitch would only weigh a single gram, but an elephant balancing on a pencil would not break through a sheet as thick as Glad wrap. The material is just a single atom thick, meaning that it takes very little matter to create large quantities of it. And the strength is due to the uniformity of the carbon lattice with flexible but strong carbon bonds within it. While being incredibly cool, there are also many life-saving and practical applications of these materials, such as filtering dirty water. Recently, a new type of filter that is capable of filtering liquids at 9 times the rate of previous commercial filters has been developed by the universities of Kentucky and Monash. These filters work by utilizing the spaces in the graphene lattice to filter out any unwanted contaminants. Filters such as this are invaluable in disaster situations where pure water is scarce. Using this technology, we could greatly enhance our disaster relief capability by replacing our current and ineffective methods. Another potential use of 2D materials is to clean up radioactive waste. Rice University and Lomonosov State Moscow University discovered that when introduced to radioactive water, graphene oxide flakes will quickly bond with and solidify many forms of man-made and naturally occurring radiation. It is easy to produce in large quantities, and the technology is key to combat many issues involved in nuclear energy. Graphene oxide could potentially be used in the cleanup after the 2011 Fukushima disaster in Japan, an area still contaminated with deadly plutonium and other radioactive isotopes. Because of their incredible strength and weight, these materials can also be integrated into many composite materials to make them stronger and lighter. The flexibility of graphene means it can be used in many different ways. One important place where these materials could be integrated would be in airplane chassis. Where currently steel is used, graphene composites would make stronger and lighter planes, making them more efficient, faster, and more environmentally friendly. As a country, we have a strong aeronautical engineering field, and we could be at the forefront of this technology, developing it for use overseas and at home. 2D materials are soon to become a massive industry, and our small country does already have a foot in the door, with universities nationwide, including our very own Victoria University, working with nanostructures and 2D materials. We have a great potential to invest in this growing industry with great scientific and economic dividends. Just like many new technologies, the current barrier preventing 2D materials, though, being mass-produced and used is the cost, as it simply isn't economically viable to have factories of people working with pencil and tape all day long. But new advances are proving production techniques cheaper and cheaper every year. Glasgow University has recently cut the costs of producing graphene 100 times by using new processes involving different and more readily available technology. Because it is a relatively new field, we could work at the forefront of research and production, making graphene cheaper and more effective. Demand for 2D materials is set to skyrocket as the new technologies are developed and this would have great economic benefits for New Zealand. With so much still to discover about this growing field of science, we can only wonder where it will take us. Who knows? Maybe in some distant future, this 2D dream will be a 3D reality.